Now that we've computed velocities for vector-valued functions, it's often helpful to think about the kinds of questions we would want to answer in relation to that velocity calculation. So imagine a vector-defined position here, and we have the first coordinate, of course, representing our x position, and our second component representing the y component. As a quick test, memory check, which of the following values is the velocity given that position function? Take a moment to answer that, and then we'll continue. All right, if we apply our derivative rules, the easy derivative is the second component, the y, which is going to be 1. And so it's definitely not d. And then if we take a careful look at the other terms, they all have a -1, or they should have a -1, which means this one's most likely the case, and not these ones. And we can also double check that when we differentiate just the x component, 1/3 t cubed minus t, we're going to get 1/3 times 3t squared minus 1, and that does indeed simplify down to t squared minus 1. So we're looking at c as our velocity function given this position function or trajectory. Looking at this formula, we can see that, well, we're moving in different directions at different times. The velocity points in different directions at different times. What we might be interested in is special points where the velocity is purely vertical or maybe purely horizontal. Let's take a look at the upwards or downwards scenario and think about how you would identify that in the algebra. If we wanted a vector that's pointing just up or just down, how would we know to identify that particular characteristic? Take a look at the options there for a moment, pause the video if you like, and then we'll check in. All right, hopefully the answer was visible here. If you think about the components that would be represented in these kinds of vectors, these would have a 0 component in the x, I'm not going left or right, and then some other number in the y component. The key thing is that the horizontal component would be 0, and it's that the velocity has that 0 component. The whole trajectory is going like this. We don't know where it is in space, but if we care about movement, that means we're focusing on the velocity. Now going back to our original function here, can we identify a point where the particle is moving in a perfectly vertical direction? Well, what we just said was vertical direction implies that the velocity in x is equal to 0, and that means that t squared minus 1 equals 0. Just looking at that, hopefully you can identify some candidates on the left-hand side here. If you like, take a moment to pause, then we'll finish it up. Okay, here, this is a perfect square. We can factor it and still have it equal 0, and that's going to give us two solutions, t equals 1 and t equals -1. So that would be our D answer. And it never hurts to confirm. If we take the velocity at time 1, it's going to be t squared minus 1, 1 squared minus 1, that's 1, or 0, 1 rather. And that would be a perfectly upright vertical velocity vector. And v of -1 is going to be hauntingly similar. -1 squared is 1, -1 is still 0. The y component is still 1. So both of these would be pure vertical, and as it turns out, for pure upward velocity vectors. And again, in many applications, it's important to be able to identify those particular characteristics in the graphical sense, and then use the algebra to identify exactly when or where they occur.